Good morning, Chemistry 20s. Today I wanted to talk to you guys about this way of writing molecular shapes called the VSEPR, VSEPR theory. And so we're in this notes guide, which you would have picked up just new. So the problem we face is, how do we write out 3D molecules? We want to show their shape. They're three-dimensional, but we're writing them on paper, which is two-dimensional. So how do we show the shape of the three-dimensional molecule? We have to use this VSEPR theory. And VSEPR theory stands for valence shell electron pair repulsion theory. What does that mean? Well, it means that electrons, because they have the same charge, they're negative, are going to repel one another. They're going to try and get as far away from one another as they possibly can. So how do we do these shapes? How do we predict them? Well, here's the rules that we're going to be using. Our first step is we draw our Lewis, our electron dot diagram for the molecule, and it's the central atom that is the most important, right? And so we're looking at the number of bonding pairs around the central atom and the number of lone pairs around the central atom, and then we add those two up to get the total number of pairs. So I'm going to come back to beryllium and boron. They're exceptions to the octet rule, but most of our examples are going to follow the octet rule. And we are going to be needing to use this chart a lot. You're going to be coming back to this, table 7. You're going to memorize it. Super awesome, important table. And it goes through and it shows you the formula, the number of bonding pairs, lone pairs, etc. You're probably wondering, like, what the heck? What do you mean by AX2 or AX3? Well, what does that mean? Let's look down here, and it says that here's a molecule showing A as the central atom. The X's are the peripheral atoms, the outside atoms, the other atoms, and then E is the lone pair. And then when we're drawing our diagrams, a bond that is in the same plane of the paper is a normal straight line. Dashed line means that the bond is extending backwards away from you, like into the screen away from you. And then this wedge-shaped bond means that it's sticking out of the paper facing you. So we're going to take a look at an actual example from our notes guide here. And we're going to the next page on to PF3. So 1 phosphorus in this, 3 fluorines. Every phosphorus, group 15, is going to have 5 electrons in its valence shell. Every fluorine atom is going to have 7 electrons. So the total number of electrons that we're looking at in our diagram is 26 electrons. Now we have to figure out who is this central atom. So we draw out our Lewis structures. Phosphorus, with its 5 electrons, can make more bonds because it has 3 bonding electrons. Okay, 1 lone pair, 3 bonding electrons. Fluorine can only make 1 bond. So our central atom is PF3. So we start connecting our fluorines, our peripheral atoms, to the phosphorus, and then we are going to complete the octets for everybody. So now we've got our PF3, there's our Lewis dot diagram. Now we start having to look at how many bonding pairs do I have? Well, here I have 1, 2, 3 bonding pairs. I showed those in yellow, and then 1 lone pair. 3 bonding pairs and 1 lone pair makes for a total of 4 pairs. So what do we do now? Now we go to our chart on table 7. 3 bonding pairs, 1 lone pair, total pairs 4 gives us a general formula, AX3E. What does that mean? 1 central atom, A. Well, who is that? That is this guy, the phosphorus. There's my central atom. X3, so there are 1, 2, 3 peripheral atoms, and then there's this huge lone pair of electrons. We typically don't show it, but that's E. That is the lone pair of electrons. What do we call this? We call it trigonal pyramidal, and this would be its stereochemical, its 3D shape. This guy follows the octet rule. So I'm going to come back with another video. In the meantime, if you want to email me, michelle.ledeen@ghsd75.ca. Thank you guys, and we'll see you in our next video.